Hi, my name is Tom Brazier. I'm with Grantham University. My student ID number is G00084861. I'm here this evening to discuss my data acquisition system circuit. I have a slideshow, I have a circuit, data acquisition circuit, and I also have a multimeter reading the voltage off of my Wheatstone bridge. Data acquisition systems are used everywhere in the world, many different applications, including at military test centers to test vehicles for the strength of their armor packages. This is a block diagram of a data acquisition system. It includes the equipment under test, which when stimulated, it exerts a force on the Wheatstone bridge sensors. The Wheatstone bridge sensors then produce a voltage that is seen by the data acquisition circuits. It's signal conditioned and sent off to a personal computer for data analysis. This was my original data acquisition system circuit design, but I had to change it because there weren't any ADCs available from the vendor. This included a Wheatstone bridge, a differential amplifier, the ADC, and a series of LEDs. I then changed my design to include a voltage divider ladder, a bank of comparators, and an encoder. This functioned the same as an ADC. Before I go on to the description of the different modules within the circuit, I will go ahead and run the circuit simulation software. I am going to read a voltage off of my Wheatstone bridge. As I change the potentiometer, the voltage will increase. These multimeters here are connected to the nodes on the voltage divider network. As I increase the resistance of the potentiometer, the voltage increases, and as it makes its way through these levels, the comparators will send a signal out to the encoder. The encoder then changes those signals into a binary signal. So as I increase the potentiometer, you will see the indicators light. That's a binary 1, binary 2, binary 3, binary 4, 4, binary 5, binary 6, and binary 7. So in my circuit, I have a power supply that includes a 9-volt battery and a 9-volt to 5-volt voltage regulator. The 5 volts supplies the entire breadboard circuit. This is a diagram of a Wheatstone bridge. These components here are my Wheatstone bridge. As you can see, there are 4 precision resistors and a potentiometer, which I used in place of my strain gauge due to financial reasons. This shows a balanced Wheatstone bridge where the current G is equivalent to 0. That means that there isn't any current going through this branch. That also means that voltage at node A is equal to voltage at node B. This is a description of the ADC. It uses comparators and an encoder, as I did. This is a description of a comparator. It's a device that compares two voltages or currents and switches its output to indicate which is larger. Here's a pictorial representation. This is a description of the voltage divider network. Voltage divider network is a linear circuit that produces an output, V out, that is a fraction of its input voltage, V in. That's all dependent upon the resistances of these two components. An encoder is a device or circuit that converts information from one format or code to another. That's this microchip here. This is the internal makeup of the encoder. You have 8 inputs and 3 outputs. It's made up of OR logic gates. This is a truth table for an encoder. It has 8 states, inputs, outputs. This column here has a weight of 1, this column here a weight of 2, this column here a weight of 4. That provides a binary output. So this row here has a value of 0, a value of 1, binary 0, binary 1, binary 2, 3, 4, 5, 6, and last but not least binary 7. So the circuit output can be seen on a series of LEDs. It also includes 3 current limiting resistors. And now I will show you the operation of the circuit. As I increase the potentiometer, it's going to increase the resistance in the Wheatstone bridge. The multimeter will then see that difference in voltage, and it's going to be about a change of about 80 millivolts. You will also be able to see the change in the LEDs here. Now I will do one at a time because with the multimeter connected, it will load down the circuit and you will not get an accurate representation on the LEDs. So this is where we will use the multimeter first, and as you can see, as I increase the resistance, the voltage increases by about 80 millivolts. That's the max. I'll reset it, disconnect the multimeter, and show you the output on the LEDs. That's binary 1, binary 2, binary 3, binary 4, binary 5, binary 6, and binary 7. This is a chart that shows the circuit verification. As you can see, you have the R5 values, which is my potentiometer, and that ranges from 0 to 18 ohms. As you change that, you will get the measurements as I just showed you. I did some hand calculations and compared it to the circuit simulation results, and they are pretty much identical. The actual measurements that I read off the multimeter are a little bit lower than those. This shows you the voltages at the voltage dividers. Here in the schematic, it would be these nodes here, and these as well. And the actual measurements were a little bit lower than the hand calculations and the circuit simulation. Everything went pretty well with the project, but I did have a few issues. I started out with a scope that included a data acquisition system that you might see at an Army Operational Test Center. So this included personal computers, rack-mounted test equipment, signal conditioning systems, multiple transducers, with a budget of like $228,000. So I simplified that into a circuit, as you can see here, which was more realistic for the scope of the class. Another issue I ran into, which I had mentioned earlier, was I could not find an ADC from the vendor, so I had to use comparators and an encoder in place of the ADC. And the other issue was the strain gauges were just too expensive for the project, so I used a potentiometer in place. This is my cost analysis breakdown. As you can see here, it includes my strain gauge, which was $73. That ended up giving me a total price for the project of $127.81. Without the strain gauge, the cost of the project was only $54. So in conclusion, the implementation of data acquisition systems at military test centers helps save the lives of our soldiers in the fight against IEDs. That concludes this representation. Thank you very much.